Okay, so the material for this part of the lecture comes from chapter 8 and chapter 17. You should think about this in tandem or in concert of the material that I've gone over in chapters 1 through 4. The material in chapter 8 that I'm interested in for the upcoming exam is on pages 202 through 210. So we're not even covering the entirety of the chapter. And really what I'm interested in the class knowing and understanding are the properties of the bell curve or the normal distribution. So if you remember from chapter 1, the two main branches of statistical analysis are descriptive statistics and inferential statistics. For descriptive statistics, we have measures of central tendency, measures of dispersion. We have some visual representations like the frequency distribution and histograms. That's all necessary and important to use to better understand our data, whether it's a sample of a larger population or whether or not we've measured the entirety of what it is we intend to measure. So everybody attending a football game or a party or something like that, like taking a poll of everybody in a student group or everybody in a meeting. So when we are engaging in statistical analysis, we make assumptions. We make assumptions about the generalizability or representativeness of our sample to the population that we're interested in. And we really hope that our sample looks like our population. Like if we were interested in all the fifth graders in the Bahamas, then we should take a sample that has very similar descriptive statistics as that larger population. Now, when we come down to it, sometimes that larger population, we don't have access to data about it. We have to make certain assumptions. So really, a lot of statistics involves this word assumptions. We assume that our data are normally distributed. We assume that our sample represents our population. We assume that there are similarities in the measures of dispersion between the various groups that we're interested in. So the normal curve serves as the basis of one of the major assumptions in statistical analysis. This is also called the Gaussian distribution, the normal curve, or the bell curve. It's something that I know that you've seen before in this class and in certain discussions, maybe in other classes as well. As the reference here, says, you might remember from chapter 4 that if the median and mean are different, that you have skew in one direction or another, that your data could be skewed. So one of the features about the bell curve of the normal distribution is that it's, first of all, it's shaped like a bell. So it should be somewhat symmetrical. Maybe it looks like a hat. They could call it the hat distribution if you can see a hat in there. But the mean, the median, and the mode all need to line up, which means that, for example, if I give you a set of descriptive statistics and I ask you to tell me whether or not the descriptive statistics represent a normal distribution, if the mean, the median, and the mode are not the same or very, very similar, then they are not normally distributed. So the mean, the median, and the mode will not be lined up if there is skew to the right or skew to the left. In the case of skew to the right or a negative skew, the mode will be more than the median and the median will be more than the mean. If you have a left-leaning skew or a positively skewed distribution, the mode will be less than the median and the median will be less than the mean. And that always follows that pattern. So there are known patterns about distributions based upon the descriptive statistics that we've been going over. So what I want you to know for the exam are some of the essential features of the normal distribution. You should just be able to tell me what these features are, that there's symmetry and that the mean, the median, and the mode all line up at the center. And also you have what's called an asymptotic tail. Now this is probably a new word, but don't be afraid. It's a good word. It just means that the tails extend on into infinity. They go on forever. So they never quite touch the horizontal axis. And why is that? Well, it has to do with some mathematical properties and things of that nature, but also has to do with some philosophy of science, in that we're trying to allow for the minute, minuscule possibility, however improbable it might be, that some fantastically extreme event could occur. Think about like if you've seen these new Marvel movies like Ant-Man or Doctor Strange, the fantastically impossible multiverse or quantum world or something like that, where something very, very, very out of the ordinary happens. We allow for that possibility with the asymptotic tail. Just the tail is the third feature to know. It's just saying that you have a near infinite and probably infinite set of possibilities, though the probabilities become nearly infinitely small. Like you're almost never going to see something way out beyond the third or fourth standard deviation. So those are essentially the three basic features of the bell curve that you need to be familiar with. There's one more set of features that point to the normality of the bell curve. And these are how the values of the proportional ranges are distributed. And so hopefully this looks a little bit familiar to you. If I can get the book to cooperate with me, it is stuttering because apparently my computer doesn't have enough RAM or something. This would be that between one standard deviation below the mean and one standard deviation above the mean, you'll have about 68.2 or 68.26% of cases. So you can say 68.3, 68.2, 68.26. You see all these numbers. Sometimes you even say, you see people just say, 68, and that's fair enough because 68.2 rounds down to 68. Between two standard deviations below and two standard deviations above the mean, you have about 95% of all cases, or 95.44% of all cases. So that's what the curve is representing. The curve is actually representing the proportion of data points that you would see within the standard deviations. Now, the standard deviation is something you calculate yourself. So let's say that we're interested in this data set right here. You should, at this point, be able to tell me what the calculated standard deviation of this data set is, based upon the information available to you. I can tell you it doesn't have anything to do with the percentage of possible cases within the ranges, because that never changes. If it's a normal distribution, these numbers right here do not change. You're always going to have 68.26% of cases within one standard deviation above and one standard deviation below. These values, negative 321 and positive 321, they don't change either, because these are essential features of the normal distribution. So you should be able to infer what the standard deviation is. And if you said 10, then you are correct. You either read it down here, or you could see that our raw scores differ by 10 every time you change one standard deviation above or one standard deviation below the mean. So we know that the calculation, like whatever your data set would be for the data being used to represent this example, the calculated standard deviation would be 10. The calculated mean, median, and mode would be 100. Because it's a normal distribution, all three of those measures of central tendency would align at the middle. And in this case, whatever it is that we're dealing with, whatever example amounts to 100, whether it's IQ or number of ice cream cones you eat in a year, whatever it is that you're measuring, 100 would be the mean. And the standard deviation is 10. So one above the mean is 110, two standard deviations above the mean is 120, and three standard deviations above the mean is 130. It would be very, very unlikely to see anything 4 standard deviations above the mean. And it has everything to do with the properties of the normal distribution, because 99.7%, actually 99.877.8%, more than 99% of all cases are between the first 3 standard deviations. So this is something you can calculate yourself, 99.74. So let's add up all of these numbers, 2.15 plus 13.59 plus 34.13 plus 4.13 plus 13.59 plus 2.15. And we have 99.74, excuse me, earlier. So more than 99% of cases are between these standard deviations. What happens if we add the remaining values in that diagram right there? Plus 0.13 plus 0.13 equals 100. So basically what they're telling you is, like, if you push these figures on out into an infinity, you're going to capture every possible case. Now, theoretically, it is possible to see something far out in the distribution, but in reality, it's not likely. So we have figures like this. And like I said, from time to time, you'll see slightly different numbers used to represent the calculations, because there are mathematicians and statisticians out there who say, but if we use a slightly different way of measuring and calculating and inferring from statistical procedures, we have these slightly different numbers. So the field of statistics is alive with debate and controversy even to this day. But generally speaking, those are the properties of the normal distribution. You have symmetry. The left and right sides from the mean are the exact same proportions. That's why all the numbers are proportionally the same on both sides. You have the mean and the median and the mode line up at the center, and you have asymptotic tails. Furthermore, you have a division of this the standard curve or the normal curve into standard deviations. And as we'll come to see in weeks ahead, this is what will allow us to make comparisons between groups, because we can standardize the scores of any given group. We can standardize them relative to these numbers right here and these numbers right here. So it doesn't matter what our raw scores are, as long as we can plot the standardized versions of those scores. So essentially, that is what I want you to know from the material in chapter 8, are the properties of the normal distribution. Because once you have mastered an understanding of those properties, then we can move forward with some more of our assumptions. And so you can read a lot more about that material in these sections. Like, it's the author of your book is basically going to describe the same thing I have in slightly different language. These blue tables are always useful for condensing and summarizing material. But for the upcoming test, I just want you to know the material between pages 202 and 208. Let's see. Yeah. And so this is what I was saying earlier when I calculated the proportional values. For any distribution of scores, if the scores are distributed normally, and that's a big if, that's one of our assumptions, almost 100%. Now, almost 100%, depending upon the numbers that you use, of the scores will fit between -3 and +3 standard deviations. So that's it. You're not likely to see anything greater than -3 or +3. And it's because of the way that the normal distribution occurs. So again, it's a theoretical construct that we use to test our scientific research hypotheses and research questions. It's kind of a standard or a benchmark. And in the weeks to come, we'll learn that there are other things that we do in science that are fairly similar. So when we do hypothesis testing, we make some assumptions based upon how it is that many aspects of reality tend to be distributed. So for example, one more time, like, the reason that you see the large hump in the middle is because it's a visual representation of the proportion of cases that you would see centering on the mean or the average, all three measures of central tendency. So you have like moderately smart people, moderately short or tall people, like how fast people can run, the average speed that people drive on a highway, in many different cases are going to be distributed in this way, where just about 2/3 or 68% of the cases are average, are within one standard deviation of the average. 95% of all cases are within 2 standard deviations of the average. And then over 99% of cases are within 3 standard deviations of the average. So again, all of that undergirds or serves as the foundation of some of our most basic statistical assumptions when we go to do inferential statistics. But this is not always the case. Sometimes you don't deal with statistical properties that that meet these assumptions. So, for example, like one of the most basic assumptions that we have when we're dealing with material that involves normal distributions is the ability to calculate the mean and the standard deviation. As I've discussed several times in this course, if you are working with nominal or ordinal level data, you cannot calculate a mean. You cannot calculate a standard deviation. Those are not features, or those are not properties of that scale of measurement. And so if you cannot calculate a mean, there is no distribution, there is no symmetrical distribution. There's nothing at the center. You're dealing with such skewed data that you need another set of assumptions. And this is where non-parametric tests come into play, along with tests that deal with relatively small samples. Okay, so this has 4 smiley faces, this chapter. So the author is saying this is easy stuff. So do not be intimidated. We're gonna take our time to try to understand why would people consider this to be easy. Okay, before we get to the chi-square though, the author has decided to introduce you to some sort of to another couple branches in statistical analysis, and these are what are called parametric and non-parametric statistics. So in parametric statistics, we basically use the assumption, we're operating under the assumption that our sample represents the population. So the sample is large enough to represent the population. In statistical analysis, this is oftentimes around 30, like 30 to 100 people. You don't need many more than 100 in psychological studies in order to represent like a sociological population like the United States or a larger country like that. You need a few more people. You need around 1,000 to 1,100. But in many statistical analyses, you'll see 30 people used to represent much larger populations. So in parametric statistics, you have a parameter. That's where the word parametric is coming from. You have a parameter. And what is that parameter? Well, your population of interest is the parameter. If we were interested in studying all of our beloved 5th graders in the Bahamas, that would be our parameter. So that's our population. So we now know what we're trying to represent, all the 5th graders in the Bahamas. If we're interested in representing the Bahamian population, now we know what we're representing, all Bahamians, all living Bahamians. Now it'd be slightly different if we said all people in the Bahamas, because that includes residents, non-residents, tourists, perhaps some unauthorized migrants. And that might be a little bit more difficult to represent. And that's one of those aspects of statistics where you need to keep in mind that you are communicating with other people. So if your parameter is a given population, then you need to communicate to your audience that you've adequately represented that population. Another feature of parametric statistics is that you have comparable variances. And so here's this word variance that I showed you from chapter 3. This is basically one step away from being the standard deviation. The only thing that you don't do is take the square root of the standard deviation and you have the variance. So you could essentially say standard deviation here, but you're saying that the dispersion or the variability within the groups that you're interested in is very similar, or it's homogeneous. Because if the dispersion or the variability is different enough in the 2 groups, in your sample, your population, or in any 2 groups that you're comparing, then you're not really comparing apples to apples. You're not comparing two equal groups. There's something fundamentally different about the groups, and now you've violated an assumption about your data. So then you would need other statistics, and those other statistics are non-parametric. So sometimes you don't have a large enough sample. Sometimes you only have 20 people or 10 people. Sometimes you don't have normally distributed data. You have skewed data. So you have a mode that is way above the median, that's above the mean. You have a mode that's way below the median and way below the mean. So sometimes you violated the assumptions involved in parametric statistics. The majority of this book, when we get to inferential statistics, the majority of that is parametric statistics. That's just what we're going to be doing. But again, even the author of this book is like, well, look, even back in chapter 2, we covered some information regarding the nominal scale of measurement. So you can see that statement right here. And this is another aspect of non-parametric statistics, is that like sometimes you are measuring participation, or you're measuring the numbers of people in different categories. So the number of Jews, Catholics, Muslims, the number of Bahamians, Jamaicans, Trinidadians, the number of boys, girls, the number of FNM, PLP, Democrat, Republican. So people who represent different categories. Those are nominal levels of measurement, because we're just naming categories and then counting the mode, or how many people are in each category. So the most people in a category. So this is where we would use the non-parametric technique called chi-square. So chi-square is kind of a more general term for some statistical procedures that come in two different flavors. The flavor that we're dealing with for the upcoming test is the goodness of fit test. So this is just about the most simple statistical procedure that you can do. So what we're doing here is we're saying, okay, like let's say that we went out and we measured the level of education of some people, let's say at the mall or at a sporting event, or who are employed for a given firm or for a business, right? And for whatever reason, we're interested in level of education. We say no college, some college, college degree. And this is what we actually observe. So if that's what we actually observed, and I actually had my calculator still up, we would see that we have 25 plus 42 plus 17 people. So we have 84 people total that we've asked what their level of education is. So these 84 people represent this particular distribution. We can see that there's some order, like there's an orderliness to having no college, to having some college, to having a college degree. And we might make some basic assumptions like, well, maybe these are younger people and these are young adults and these are older adults, or something of that nature. Certainly if we were at a place with a more homogeneous age group, like think of a retirement home, like where there's mainly people 65 and older, that assumption would fall flat. So really what we're doing is we're just focusing on what it is that we've observed. And one of the things that we've observed is that there are 25 people with no college, 42 people with college, and 17 people with a college degree. Okay, so what? Well, what we want to know is if this particular distribution is random, or if there's some pattern to it. Like if there was a pattern to it, right, we might think like, well, maybe the reason that we're seeing 42 people with some college degree is because we are at an event that had a lot of people between the ages of 18 and 24, which typically represents the average college student. Like the average age of college students, it has a range to it. The range can be 17 to 70. I mean, and I'm just kind of making numbers up. I don't know what for sure the average college student's age range is, but foreseeably anybody who's graduated high school can go to college. So maybe what we've done is we've accidentally stumbled onto a situation where there's just a lot more people between the ages of 18 and 24, and therefore the reason that we're seeing more people with some college is because they haven't completed their degrees yet. They're still working on their college degrees. But then we would ask ourselves, like, well, then why do we see so many people with no college? Well, it could be that, some of the people are either still in high school or that they never wanted to go to college in the first place. Whatever the situation is, we can come up with a logical explanation. But what we want to do is we want to come up with a statistical evaluation of the distribution. We don't want to use our common sense or hunches or educated guess. We want to use an analytic technique to help us ascertain the quantitative nature of this distribution. And that's what the chi-square does. So after this test, we'll get to these ideas of like being significant above the 0.05 level. Right now, I'm just kind of trying to introduce you to one of the statistical procedures that tends to be a little bit easier to do than some of the others, or at least a little bit easier to comprehend the nature of. So once again, we're introduced to some symbolic notation. That would be chi-square. So this is the Greek letter chi, and we're squaring it because for whatever reason, we have squared the values that we have when we compare our observations with our expected results. So our observations, the observed frequency, and the expected frequency. Now that's the expected frequency, that's pretty much the only thing that you really have to know and understand about the goodness of fit test. The goodness of fit. Like what would be the, how can we assume that there's some expected frequency of people without or with college degrees? So I'm trying to scroll up. So if we have the observed frequencies, like here we see 25, we see 42, and we see 17, how do we compare that with something like expected? Well, this is where we have another assumption. And that, again, has been the theme of today's lectures, is some embedded assumptions in the way that we're doing our calculations. So here, the data is a little bit easier to work with, because before, like we had three categories: no college, some college, and college graduate. And what you do to get the expected results is you divide by the number of categories. So divide by 3. So you have 28. This one you can do in your head. You should be able to divide 90 in your head by 3 and come up with the result that 30 would be the answer. Now that's maybe an assumption on my part. But if you have 90, right, you say 23 plus 17 plus 50 equals 90. What do we do with that? Well, because there are 3 categories, for, maybe, and against, we divide by 3 and say, if there were an even distribution, there would be 30 people in each category. But we don't see any good distribution. We see the distribution that we have in front of us, like the actual data, the actually observed data. And so 30 would be our expected value. And why do we have that? Well, after this first test, we'll come back to this notation right here. So this is probably a little bit new to you, but all I want to point out right now is the equal sign, is that there's an equality sign, which basically says that if our null hypothesis is true, we would see equality. At this point in the semester, I just want you to know that this right here is that we will compare our observations from our expected results, square the numbers, divide by our expected numbers, and we'll come up with the chi-square. Pretty much it. This is pretty much just getting you to tell me what is the expected value. That's about it at this point. That will satisfy me for the first exam.